In this video, we are going to be treating amino acids. We are going to be treating amino acids and their reactions. But before we go ahead, I really want to thank those of you who have taken your time to subscribe to our channel. But those of you who have not subscribed to our channel, please motivate us by subscribing to our channel. But do not go without hitting the notification bell. Thank you very much for taking your time to subscribe to our channel. Let's start straight away. What do you understand by amino acids? What are amino acids? What are amino acids? From the from the word amino acid, we can define amino acids as organic compounds that contain both the amino and the carboxylate functional group, and are the building blocks for proteins. I said amino acids are these are organic compounds. These are organic compounds that contain both the amino and the carboxylate functional group, and are the building blocks for proteins. In amino acids, in a simple amino acid will contain both the basic amino group. It will contain both the basic amino group. Let me say the basic amino group, the basic amino group, basic amino group, the basic amino group, which is NH2, and the basic amino group, and the acidic carboxylic acid group, the acidic carboxylic, the acidic carboxylic acid group, that is the COOH, that's the COF, and this makes the amino acid to behave both as an acid and a base. I said amino acids are organic compounds that contain both the amino and the carboxylate functional group, and are the building blocks for proteins. I said in a simple amino acid, we will have the basic amino acid group and also the acidic carboxylic acid group. They are the two groups that are present there in a simple amino acid molecule. This makes the amino acid to behave both as an acid and as a base. In other words, we say it makes the amino acid to behave as to be amphoteric. It makes the amino acid to be amphoteric. A good example of amino acid, the general structure of an amino acid is like this. This is the general structure of amino acid. An amino acid could be represented in this form. It could be represented in this form, NH. Let me say NH2. Oh, oh. So that is it. That it could be represented like this. Or in this form. In this form, it could still be in this form like this. Or in this other form. Or in this form. It could be like this. The carbon bond is, the carbon single bond is rotatory. So this is a simple structure of, this is a simple structure, a simple general structure of an amino acid, As I said, it has an amino group, a basic amino group, which is this one, and an acidic carboxylic acid group, which is also this one, then with an alkyl group and a hydrogen there. So now, an example, we can name this one as, we can name this as, we can name this as 2-amino carboxylic acids. All these we can give them as 2-amino carboxylic acid. 2-amino carboxylic acid. So you see this the first carbon, and this is the second carbon, and the amino group is on the second carbon. We now say it is 2-amino carboxylic acid. 2-amino carboxylic acid. It's a 2-amino carboxylic acid, and until this arrow is substituted by an alkyl group before we can have the right name for it. So now there are other examples for this. This arrow here, this arrow as you find it here could be, the arrow can be the arrow, excuse me, the arrow group can be, acidic. It could be acidic. It could be acidic. The arrow group could be acidic. That is, this arrow group here could be acidic. That is, it is containing another COO group. That is, it contains, if the arrow group is acidic, that means it contains another, this group here contains another carboxylic acid group. That is the molecule contains another COO group. So if this group, if arrow is acidic, it means that there is another carboxylic acid group attached here. If arrow is basic, sorry for the interruption. As I said the other time, I said the arrow could be an acidic, that is containing another carboxylic acid group. The arrow again could be basic, that is the molecule contains another amino group. Could be basic, it could be basic, it could be basic, that is the molecule contains another amino group. It contains another amino group. Or it could still be neutral. The molecule could be neutral. The molecule could be neutral. The molecule could be neutral. That is when arrow is an alkyl group. When arrow is an alkyl, it's an alkyl group. When arrow is an alkyl group. However, there are some examples. We have some examples of amino acid. We have some few examples of amino acids. A good of them, we have alanine. We have alanine. Examples of amino acid. Amino acid. We will have one. We have let me say alanine. Two. We have arginine, or you can call it arginine. Three, we have asparagine. Asparagine. Four, aspartic acid. Could have aspartic acid. Aspartic acid. Aspartic acid. Five, You have cysteine. 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 You may have glycine. Glycine. Glycine, and many others. There are many others. These are just a few examples I can give you. Alanine, arginine, asparagine, aspartic acid, cysteine, and glycine. These are some examples of the amino acids. These are some examples of the amino acids. Uh, uh, their structures can give a good a structure of an example of, let me say, a glycine. A structure of this one. A structure of an example of it is amino ethanoic acid, which we can structure to have it as O. We can call amino ethanoic acid. Amino ethanoic acid. Amino ethanoic acid. You have the structure is in this way. We have as we have the carbon atom, the central carbon atom, COOH. So this is amino ethanoic acid, which could equally be written as H like this. So we say it is amino ethanoic acid. This is the amino group on the second carbon. On the second carbon, the amino acid, the amino group on the second carbon, and there are two carbons there. We say amino ethanoic acid as glycine. So another example that of it is a structure alanine. Alanine. Let me give you the structure for alanine. Alanine is 2-aminopropanoic acid. Alanine. Alanine is, we call it 2-amino propanoic acid. Propanoic acid. Alanine, 2-aminopropanoic acid. This structure is like this. It has 3 carbon atoms there. It has 3 carbon atoms there. It could be written in this form. Yes, a methyl group. It's a methyl group there. So as I said, it is the first carbon, the second carbon, and the third carbon. So the second carbon, the amino group is on the second carbon. This is carbon 1, carbon 2, and carbon 3. The amino group is on the second carbon, and we say it is 2-amino propanoic acid. It could also be written like this. It could also be written as, it could also be written in this form. The methyl group could be here, since it is rotatory. You can write it like that. You can say it's 2, in this form it is 2-amino propanoic acid. 2-amino propanoic acid. So these are just examples of structures of the amino acid. So now we will be trying to see some reactions of propanoic acid, of amino acid, some reactions of amino acid. So now reactions of amino acids will include, let me just write it, reactions of amino acids. Reactions of amino acids. Now you should know that amino acid will undergo most reactions of the amines. The same reaction that amines were undergoing, amino acid will undergo. Amino acid will also undergo the same reactions that most of the reactions that carboxylic acids were undergoing. Why so? They will undergo the reaction of the same most of the reaction of the amine because of the amino group in them. They will also undergo most of the reactions of the carboxylic acid group of carboxylic acid because of the presence of the carboxylic acid group in them. So that is why they will undergo some of the reactions of the amine and the carboxylic acid. Amino acids are amphoteric. You know this very well. Amino acids are amphoteric, and because I say they are amphoteric because they have both acidic and basic property. They are amphoteric. They have both the acidic and the basic property. Why do I say so? Because of the presence of the acidic carboxylic acid group in them and the basic group in them. The amino group, which is has the property of basic property, the carboxylic acid group that has the acidic property. In that case, this makes amino acid to be amphoteric. It should be noted that the amino acid molecule interact within itself due to the basic and the acidic group. It interacts within itself. I said the molecule interacts within itself. The molecule interact within itself due to its basic that is its basic property due to its basic group due to its basic group, and the acidic group. Acidic group, and this is the acidic group in it. So how does it happen? How would the molecule interact within itself? How would an amino acid molecule interact within itself? This is what happens. You will see that, let me just write here so that you can easily see it. Let me say we have this molecule here. We have NH. I have an NH2 here. We will have it here, and this other place here. So what is happening here is this is what is happening here. That is what is happening. Here in this molecule we call it a zwitter ion. This is a zwitter ion. This is a zwitter ion. This is a zwitter ion. So this is what is happening. Let me just tell you what is happening here. You see that the carboxyl group donates a proton. The carboxyl group donates a proton to the amino group. The carboxyl group donates a proton to the amino group, and the amino group accepts the proton, and a zwitter ion is formed. The ion is called a zwitter ion because it contains two regions of positive and negative charge. This is a zwitter ion. The presence of the zwitter ion means the amino acids are soluble in water. As we said, the molecule interacts within itself due to the basic and the acidic groups that are present there. And in this group, we are saying that the carboxyl group, this is the carboxyl group here, it donates. This is the carboxyl group, which is the acidic group. Being an acid, acids are proton donors. So in that case, they will donate a proton. This group will donate a proton. It will donate this proton here, donate the proton to the amino group. On the amino group, there is a lone pair of electrons on the nitrogen. So now, the carboxylic group will donate a proton to the amino group. The amino group now accepts the proton, and a zwitter ion is formed. It is called the zwitter ion because there are two regions here. There are two regions here. There are two regions of positive and negative charge. The zwitter ion, the presence of the zwitter ion means the amino acids are soluble in water. The presence of the zwitter ion means the amino acids are soluble in water. So I can just include it here. Let me just put it here that I can just put it here that the presence of the presence of the zwitter ion, the presence of the zwitter ion means the amino acid is the amino acid, or it means that the amino acid is soluble in water. Is soluble in water. So we cannot say that amino acids are crystalline solids. Amino acids are crystalline solids that are soluble in water. Amino acids are crystalline solids that are soluble in water. So a solution of amino acid in water contains zwitter ions. So any amino acid you put in water will contain zwitter ion. Why do I say it will contain zwitter ion? We say that because of the two groups there, the acid group and the basic group, the acid group will donate a proton to the basic group, and the basic group will accept the proton. As a result of that, a zwitter ion is being formed. So that is just the simple fact of it. So the reactions, as we said, so in this reaction they resist. One thing is that amino acid resists any change in pH when small amount of acid or base is added to them. So we can now call them as buffer solutions. Amino acid resists any change in pH. Amino acid resists any change in pH when small amount of acid or base is added to them. Let me just put it here. They resist any change in pH, when small amounts of acid or base is added to them. So we call such solutions buffer solutions. We call such solution they are therefore called such solutions are called buffer solutions. Buffer solutions. Such solutions are called buffer solutions. So now, because the amino acid interact within itself, it interacts within itself due to the basic and the acidic nature of it. and it forms zwitter ions. So because of this situation, when amino acids are in water, they resist. When they are in water, they resist any change in pH when a small amount of acid or base is added to them. Such solutions are called a buffer solution. Let me just show you how this works. Let me show you how it works. For instance, if as an acid, proton as an acid or a proton donors, as proton donors, if the pH of the solution is lowered, if the pH of the solution is lowered by adding acid, by adding a hydrogen ion to it, the carboxylate part of the zwitter ion will accept the hydrogen ion, forming what? Forming the undissociated ion, thereby removing the acid from the system or from the solution and adjusting the pH to its initial position. Well, let me just write this equation and you see how it works, how it is interacting within itself. Take for instance, we have a structure like this. H, let me say H, 3. We have carbon, we have a hydrogen, we have iron, we have this, we have a plus here. Yes, plus a hydrogen ion, that is a proton, plus a proton. We will have the same molecule again, H3, N. We'll have the carbon, the hydrogen, the arrow will be there, yeah, and what? The hydrogen. And the hydrogen there. This is what is happening here. You will have okay, there is a lone pair here. So as I said, now if the pH of the solution, this is a solution, this is a zwitter ion. I said the presence of the zwitter ion means that the amino acid is soluble in water. Because of this zwitter ion, they are in the solution. And we said they resist any change in pH when small amount of acid or base is added to them. Such solutions are called a buffer solution. How is this zwitter ion acting as a buffer solution? See how it acts. I said if the pH of the solution is lowered, if the pH of the solution is lowered, it means that it is acidic. So if the pH of the solution is lowered by adding what? By adding a proton there, by adding an acid. If the pH of the solution is lowered by adding an acid there, this is the acid. The carboxylate part of the zwitter ion, this is the zwitter ion. The whole of this molecule here is a zwitter ion. So the carboxylate part of it, this is it. The carboxylate part of the zwitter ion will do what? Will accept the hydrogen ion. It will accept the hydrogen ion. Remember that this oxygen here, the oxygen with this oxygen here has a lone pair of electron here. So this hydrogen ion will attach itself to the lone pair of electron here. So the carboxylate part of the carboxylate part of the zwitter ion will accept the hydrogen ion. And when it accepts the hydrogen ion, it reforms what? Reforming the undissociated acid. This is the undissociated acid that it has formed. Reforming the undissociated acid group. Thereby doing what? Thereby removing the acid from the solution. It does that by removing the acid from the solution. And when it removes the acid from the solution, what happened? It adjusts the pH by returning it to its initial position. So you now see that the pH has not been lowered again. The pH has returned to its normal position. Once more, I said if the pH of the solution is lowered by adding an acid there, that is the proton, the carboxylate part of the zwitter ion will accept the hydrogen ion, when thereby forming what? Thereby forming the undissociated acid group. And when it forms the undissociated acid group, it removes the hydrogen ion from the solution. And when it removes the hydrogen ion from solution, it now adjusts the pH to its initial position. That is how a buffer solution works. On the other hand, that is, this is working as what? This is working as a proton acceptor. As proton acceptor. As proton acceptor. As proton donor. I said lowering the pH. Lowering the pH of the solution. Lowering the pH of the solution. Now, raising the pH of the solution. Raising the pH of the solution. Raising the pH of the solution. This is the equation. If you want to raise the pH of the solution, this is how the equation looks like. We will have something like this. We will have something like this. And H3. We will have H3N. Yeah, the same thing that happened here will be this one. Hydrogen. Yes. The carboxylate. Yeah, it will give H2, H2N, carbon, hydrogen, arrow, carboxylate, a carboxylate, and what? Plus water. Plus water. And in that case, we will have plus the OH plus the OH plus the OH. So this is what happens here. Okay, raising the pH of the solution. In raising the pH of the solution, this is what happens. If the pH is raised, let me explain it. If the pH is raised by adding a base, this is the base, the OH is the base. If the pH is raised by adding a base, this the NH3 plus part, the amino group part, the amino group ion part of the zwitter ion will donate what? Will donate a hydrogen ion to the hydroxide. This is the hydroxide. Will donate a hydrogen ion to the hydroxide to form what? To form water. To form water. And the reforming what? Reforming this. Reforming the base group. Thus removing the base from the system and adjusting the pH to its initial position. Once more, once the pH is raised, if the pH is raised by adding a base, that's the OH, by adding a base, the OH to the solution, this group here is going to do what? This group here will do what? Will donate a proton. It's going to donate a proton here. It's going to donate a hydrogen ion from here. To what? It's going to donate this hydrogen ion to the OH group here, to the base. And when it donates the hydrogen ion here to the base, what is formed? A molecule of water is formed. And when a molecule of water is formed, what happens? It reforms this group. It reforms the amino group. It reforms the amino group, thus removing the OH from the solution. It removes the OH from the solution. And now when it removes the OH from the solution, it adjusts the pH back to its initial position. So that is the whole thing. Let me just indicate it there by maybe an arrow here, how it is working. We have the OH here. We know that the OH has a lone pair of electrons. We will have something like this. Remember, in organic chemistry, the curly arrow are indicating the movement of the lone pair of electrons. So this lone pair of electrons is for who? It's for a proton here. So one proton will leave from here and attach itself on this lone pair of electrons. And when the proton leaves from here and attaches itself here, only NH2 is left. This is the NH2, and we are back to the system again. The base has been removed from the system again. The pH has been readjusted to its initial position. That is how the whole system is working. That is how it works. Then again, we will have to go to, at a certain pH, it should be remembered that at a certain pH point, the charges are balanced. At a certain pH, the charges are balanced. That is where there is no overall charge difference. That is where the positive charge is not more than the OH, where the positive charge on the amino group is not more than the negative charge on the oxygen, or where the negative charge is no more than the positive charge on the amino group. And when this happens, this point is called what we call an isoelectric point. An isoelectric point. That is, there's neither the positive or the negative charge. Neither of the positive or the negative charge is dominating. The positive charge on the amino group or the negative charge on this, when none of them is dominating, when they are just equal. When they are just equal, we call it isoelectric point. and usually it has a pH of 5 to 6.5. And this molecule as a whole is electrically neutral. When there is no overall charge, when there's neither when there is neither when the positive neither the positive or the negative charge is dominating, when they are just equal, we call it the isoelectric point. And at this point, we say the molecule as a whole is electrically neutral. The molecule as a whole is electrically neutral. So now, I want to give you some example of to summarize what we have just taught, what we have just studied here on the acidity and the basicity of the structure. Let me just draw here so that you can remember on adding acid or on adding base. So this is the structure. We'll have something like this. We have H2N into CH into C. There is arrow. That is COO. COO minus. We have an acid and base. We go back again. I have H3. Yeah. I have hydrogen. I have arrow here. We have this. And we have this other structure here. To carbon, to arrow, let me put this. You have a lone pair of electron here. That's a charge there. There's a plus there. There's a charge there. There is a plus there. Now, let me put this. We have OH, and we have the hydrogen ion. We have the hydrogen ion, and we have the OH. In this case, we can name these to be a species. Let's put this to be a species that is a species in alkaline solution. Species in alkaline solution. alkaline solution. Yeah, high pH. Yeah, species in acidic solution. Low pH. Then here, species in neutral solution. Species in neutral solution. So here, as I said the other time, this is how we can summarize this. That I said acidity and the basicity. The acidity and the basicity. Acidity and basicity. So that is how it works. Here, as we earlier said, I said if the pH here, if the pH of the solution, is lowered by adding a hydrogen ion, what happens by adding a hydrogen ion? If the pH of the solution is lowered by adding a hydrogen ion, this is it here. If the pH of the solution is lowered by adding a hydrogen ion, the carboxylate, this is the carboxylate part of it, the carboxylate part of the zwitter ion. This is the zwitter ion. I said that the zwitter ion is neutral. Why do I say that the zwitter ion is neutral? The zwitter ion is neutral because these charges, because we said the other time that the molecule as a whole, the zwitter ion as a whole is neutral because the positive charge will cancel out the negative charge. This molecule as a whole is neutral. So now, in this solution of zwitter ion, if the pH is lowered by adding a hydrogen ion, the carboxylate part of it will accept the proton. When it will accept the proton, reforming what? Reforming the acid part of it, thereby removing the acid from the solution and adjusting the pH to the initial position. On the other hand, if the pH is lowered, if the pH is raised by adding what? By adding the base, to it. This part of the solution, this part of it will do what? Will donate a hydrogen ion. Will donate the hydrogen ion to what? To the OH minus, forming a molecule of water. There is a molecule of water that is formed here, forming a molecule of water here. The molecule of water is formed here, plus water. That is it, plus water. There is a molecule of water that is formed here, forming a molecule of water, plus it will form this plus a molecule of water. That will be a molecule of water that is formed here. Reforming what? Reforming the amino group, thereby removing the OH from the system and adjusting the pH to an initial position. So that is the whole thing. That is the whole thing. So that is how you see it. So this is the major point. This is the major point. This is the major point here. And it can react with an acid. This molecule too again can react with an acid to do what? It can react with an acid to form this. So this is the major one that is reacting. So this is it. Okay, beside that one, beside that, what we can do is that the last section here is what we call a dipeptide bond. A dipeptide bond. A dipeptide bond. What is a dipeptide bond? Dipeptide bond. A dipeptide bond is a bond. Dipeptide. Dipeptide. Peptides. Dipeptides. What is a dipeptide? A dipeptide is a compound that is formed. It's a compound that is formed from the condensation reaction between two amino acids. So when two amino acids they come together, a dipeptide is being formed. The carboxylic acid group of one of the amino acids will react with the amino group of another amino acid. When they do that, a molecule of water is eliminated, and a peptide bond is being formed. Let me just put it like a compound formed from condensation between two amino acids. This is a compound formed. I say it's a compound formed from the condensation. From the condensation reaction between two amino acids. Between two amino acids. And when this happens, what happened? That is a dipeptide. And when this happened, what happened is that the carboxylic acid group of one of the amino acid will reacts with the amino group of another amino acid. That is how the reaction will occur, and it can be illustrated in this form. I have a molecule like this, H2N. This is a hydrogen. This is arrow. We have this. Acid group plus there is a hydrogen to the nitrogen, and what will happen here will be, you will see how the reaction will be going. There is a condensation reaction between and this is minus a molecule of water. They will result in this molecule that is being formed. it will result in H. We'll have H 2 N, the same molecule, there is a nitrogen here linked to this nitrogen here. This one can come down and I'll go out here. Nitrogen to the carbon arrow, and then to the acids. And you will see here that this molecule alone this molecule alone is what we call the peptide, what we call the peptide link. What we call the peptide link, and we'll call this a dipeptide molecule. A dipeptide molecule. A dipeptide molecule, and that is how you can get it. So a recap of what we have just done here. So that is how you can get it. I said amino acids, these are organic compounds that contain both the amino group, the amino and the carboxylate functional group, and are the building blocks of proteins. They are the building block of proteins. I said they are a simple amino acid group contains the basic amino group. A simple amino acid molecule contains the basic amino group, the basic amino group, which is this one, and the acidic carboxylic acid group. And I said this molecule is amphoteric. It is amphoteric, that is behaving both as an acid and as a base. And I said that based on this structure here, the arrow can be acidic. The arrow can be acidic in the sense that the molecule may contain another acidic group, the COO group. It could be basic in the sense that the molecule may contain another amino group on it. And the molecule could be neutral in the sense that arrow is an alkyl group. So I gave an example of amino acid, alanine, arginine, asparagine, aspartic acid, cysteine, and glycine, and many others. I went further to give you a simple structure or example with structure of glycine and alanine. So a good example of glycine, which is aminoethanoic acid, I gave you the structure, how it can be written. I gave the one of 2-amino-propanoic acid. I also gave you the structure, and I told you about the reaction of amino acid, that the molecule can react within itself due to the basic and the acidic group. So in reacting within itself, you will see that the acidic group or the carboxylic acid group will donate a proton because of the presence of the double lone pair of electron on nitrogen, and forming what? A zwitter ion. When it donates a proton here, when it reacts within itself, it donates a proton to this one here, and when the one accepts the proton, what? A zwitter ion is being formed. And I say a zwitter ion is as a result of what? When there are two regions with a positive and negative charge. And I said that these zwitter ion, the presence of the zwitter ion means that the amino acid is soluble in water. And I said that this zwitter ion in solution can resist, this zwitter ion in solution can resist any change in pH when a small amount of acid or base is being added. And that's how I showed it right here. That the zwitter ion, this is the neutral in solution, is neutral. It's neutral. It can resist any change in any change when a small amount of acid or base is added. For instance, I told you about when the pH is lower, is raised by adding a base, you will see the reaction that will form, reforming these, thereby adjusting the pH. When a small amount of acid is being added, what happens? You will see how the acid, it will remove the acid from a solution by reforming the carboxylic acid group and doing what? Readjusting the pH. So you see how this solution, this zwitter ion in solution is acting as a buffer solution. And went further again to show you by lowering the pH, you saw what happened, and by raising the pH, you saw what happened. And I summarized it in this structure here. So the last one was dipeptides. I said a dipeptide is a compound that is formed from the condensation, reaction, from the condensation reaction, between two amino acids. And in these two amino acids, the carboxylic acid group of one of the acid will be reacting with the amino acid, with the amino group of the other acid. And when they react, what happens? There is a condensation, a removal of a molecule of water, leading to what? Leading to what we call a peptide linkage. There will be a peptide linkage, and this is what we call a dipeptide molecule. So thank you, listeners, for taking your time to listen to our for this lecture today. A reminder for those of you who have not subscribed to our channel, please, before you go, do us a favor to subscribe to our channel and do not forget to hit the notification bell. Thank you. Wishing you best of luck in your exam.